Hi Year 10 and welcome to your weekly introduction videos. This week we're going to look at bivariate statistics, but we're looking at bivariate data. Now, the past couple of weeks what we've been looking at is what we call univariate data. So that is basically finding the mean, median, mode, range, interquartile range, all that kind of stuff of a single piece of data that varies. So, for example, heights, weights, goals in a football match. We're looking at one set of data. Okay. This week, what we're looking at is bivariate data. So this is basically trying to see if there is a relationship between two types of data. Okay. So height and weight, and seeing if there is a link between the two, or height and goals scored. Basically, always trying to see that relationship. So we've done this before. It's basically the idea of correlation. What I'm going to try and do though is pitch it to you in a way that lines up for two reasons. Okay, we're going to talk about the idea of mathematical modelling. Okay, and it's two reasons why I want you to understand mathematical modelling. One is because the second question on paper 6 is always a mathematical modelling question, okay? And the other reason is that when you get into year 12 and 13 and you're doing your IB, you will have to do an IA, it's what I call an internal assessment, okay? And for that internal assessment, you will have to do a mathematical investigation where you do some modelling, okay? So just sort of trying to get ahead of the game and get you prepared for the idea of what a good mathematical modelling situation looks like. Okay, so we're going to understand correlation again. We're going to understand how to use a calculator to measure correlation and find lines of best fit. Okay, and we're going to be able this line of best fit, by the way, just for the purposes of vocabulary. We're going to call this a regression line. In the past, I've called it a line of best fit. Now we're going to call it a regression line. Okay. So, mathematical modelling, okay? I'd say mathematical modelling is one of the most important things that is a real-life application of the maths that you learn, okay? Now, any type of maths might be involved in a mathematical model. Okay, it's not just what we're learning this week. I think what we're learning this week will be the most simplistic type of mathematical modelling, and so that's where we start. Okay, and so it can be used to analyse almost any situation. And the reason why do we use models? Okay, we use a model to make predictions about the world in a safe way, or in a way that wouldn't be possible otherwise. So why do you build a model aeroplane? Well, you do that because it's not really safe for you with your skill sets and your age to be building a real aeroplane. But you might be interested in aeroplanes, so you build a model one, okay? We can make predictions of things going into the future, so that it's not possible to actually know what's going to happen into the future. So we use a mathematical model to see if we can predict what's happening. And we use those predictions to try and correct our behaviour or decide on a course of action based on what we think is going to happen in the future. For example, you're seeing it in the background in everyday life at the moment. Lots of mathematicians are modelling the spread of the coronavirus. So we might be able to develop a mathematical model of the coronavirus and see what impact reopening schools might have. So we can make a mathematical model that would understand what would happen if we opened schools without actually having to do it, so we can see whether that is a good idea or a bad idea before we make that decision. Okay, so obviously, given the examples I've given you, mathematical modelling is not a perfect thing. You're making predictions into the future, and predicting things is always it's got inherent reliability issues. Doesn't mean that it's completely unreliable, but you always have to consider reliability of your mathematical model. Okay, so let's get into some data. We want to devise a mathematical model that will help us predict rainfall in Lesotho. Lesotho is an African country, okay? This might be of extreme importance because if we know when rainfall will be low, then we know when we need to look for alternative water sources. So this might be really, really important to the people of Lesotho. They need to know, how much it's going to rain next month. Okay. Now, so you've got some data here from historical temperatures and rainfalls associated with them. Okay. And I've defined my variables. My x is my temperature and my y is my rainfall. Okay, so I've got two sets of data. This is why we call it bivariate data. Bivariate. Bi means two. We're looking at two sets of data and seeing is there a link between the two. Now, before you do that, you should always draw things on a scatter graph first. Okay. And actually, you can do it on your GDC, okay? So you can see here I've drawn a scatter graph. There's going to be a separate video where I show you how to do that, okay? And you should always do that first. I cannot stress enough. Before you do any modelling, you always need to look at the data first, okay? Because you can make serious mistakes if you don't look at the data first. You cannot assume what you're looking at. But it's pretty clear here that what we've got is what we would call a linear relationship. A linear relationship. It's making roughly a straight line, and we would say that there is a strong positive correlation between these data. Now, what does that mean? It means as your temperature increases, so does your rainfall. Okay, temperature is what we would, from science, we would term that as the independent variable. Independent, yeah, I'm spelling that right. And rainfall is the dependent variable. Essentially, what we're saying is that rainfall depends on the temperature. Okay, so basically, the relationship I can see there is if we get higher temperature, then we will get more rainfall. Okay. Now, some things we need to ask ourselves. Okay, we need to think about what kind of relationship is the data showing me. So we've already established that. We think it's linear. We think a straight line is appropriate for this data. I could put a line of best fit through this, no problem, and it makes sense. Okay, so it's linear. So what mathematical? It's also strong positive. Strong positive. Now, because it's strong positive, it makes sense to put that line through it. If there was no relationship, it wouldn't make sense to put a line through it at all, so you just wouldn't do anything with that data. Okay? So what mathematical model shall I apply to show that relationship? Well, I'm going to use a straight line. Y equals mx plus c. Well, all I have to do is find out what m and c are. Okay? Because I want a linear relationship. I want a straight line to go through it. Now, how strong is that relationship as well? That might be really important. Remember, if you've got data that looks like this, it's very weak. If you put a line through that, it wouldn't really make any sense. So you need some measure of how strong the relationship is. So we're going to look at that now. Okay? So here we've got some different types of relationships. Now, what I can see with just number them. 1, 2, 3, 4, 5, 6. Okay? Now, we can clearly see that the first one is strong positive. So if you ever ask what kind of relationship is, it's a strong positive relationship. This is strong negative. Strong negative. Okay, the dots are close to the line, but we've got a negative relationship. As one variable goes up, the other variable goes down. We've got no relationship, so no correlation. Okay, we've got no correlation there. Here we've got weak positive. And here we've got weak negative. And number 6 I'm going to leave for a second. I will talk about that one in a minute. Okay? Now, you'll see here what we've got is this number R. Each one of them has a number R. Okay, and this R is what we call the correlation coefficient. Okay, the correlation coefficient. And what the correlation coefficient is, and by the way, you calculate that on your calculator, and I will show you again in the video where I use a calculator how to do that. But what it shows you is both the type and strength of the correlation. Okay, so what do I mean by that? Let's just have a look. I'm going to make a table. Okay, so here's some R values. R, by the way, is always between 1 and -1. It's not possible to have an R value that's greater than 1, and it's not possible to have an R value that is less than -1, but it could be anything in between. Okay? Now, generally speaking, if it's about 0.7 to 1, then what we have is a strong positive correlation. Okay? Anything that's, say, between 0.5 to 0.7, we might class as a weak positive correlation. Okay? Anything between, well, I would say minus 0.5 to 0.5, I would say is no correlation. No correlation. There's no link between the two of them. And I think anything that is between minus 0.5 and minus 0.7 minus 0.7 to minus 0.5 is a weak negative correlation. And anything that is from minus 1 to minus 0.7 is a strong negative correlation. So we can actually put a number on it, okay? This R is putting the number on it. Okay, so you can see here, this is very, very close to 1, 0.996. So that I'm pretty confident that's a very strong relation. It's a very good model. It's very strong, very reliable, okay? And this one, again, it's almost -1, so it's a strong negative. But this one is very close to 0, indicating that there is no relationship, really, okay? And these ones are debatable, okay? We'd probably say that the relationships are so weak that they're not really meaningful, okay? Now, number 6 is a little bit different, because notice that you've got a relationship that says there's no correlation. It's close to 0. Well, what that means, actually, is there's no linear correlation, okay? So this one says that there is no linear correlation. And that would be true. However, just because there's no linear correlation doesn't mean that there is a correlation. We can see here there is a correlation. In fact, this has a quadratic correlation. A quadratic correlation. Okay, we could use a quadratic model here and it fits really, really well. Okay, so we can say something meaningful about this data. It's not linear, but it is, there is a relationship. Okay, this is why it's so important that you look at the data first. Because if all I did was get my calculator to tell me this, I might say, okay, well, there's no relationship between these variables. Forget it. Why look at it? But actually, we're wrong. There is a very, very, very strong relationship here. It just isn't linear, okay? So this R value is only testing the strength of a linear correlation, but your data might not be linear. So you must look at it on a scatter graph first. Before you do anything, always look at data on a scatter graph first, okay? Right, so again, please look at the calculator video to see how to calculate these R values, okay? I'm going to stop the video.